Hi, my name is Akhilesh, and I created a Monte Carlo simulator for multi-terminal resistive random access memory devices, or RMs. These devices are currently being researched because they can be used in new computer architectures that can perform artificial intelligence tasks more efficiently. And using my simulator, I compared two-terminal and three-terminal RM devices, and my simulation results show that the emerging three-terminal RM device type has several advantages over the conventional two-terminal RM device type that has been researched more extensively. So artificial intelligence is becoming extremely important in a number of societally important areas, from healthcare to transportation to smart agriculture. However, AI algorithms running on conventional von Neumann architectures aren't very efficient. And for this reason, there's intense research on new computer architectures that are better suited to AI algorithms. And many of these new computer architectures involve the design of a crossbar circuit to perform fast matrix vector calculations. And at the junctions of these crossbar circuits are physical memory devices, which are analogous to synapses in the human brain. And my research focuses specifically on modeling the physics of these memory devices. So this picture shows an RM device. The middle part is called a switching layer, which is typically an insulator. These three are metallic electrodes, which are used to read and write the memory state of the device. So the insulator can actually conduct because of the defects within it, which assist in the electron flow. When you apply a voltage on the gate electrode, the current will flow from the gate electrode to the top and bottom electrodes through the defect network. When you apply large enough voltage, the defects themselves will actually migrate through the switching layer, which will cause the conductance of the device to change. So during write mode, the top and bottom electrodes are grounded and the gate electrode is biased. During read, the top electrode is biased at a low voltage, the gate electrode is floating, and the bottom electrode is grounded. So 2T RMs have been researched extensively, both computationally and experimentally, for about 10 years now. 3T RMs are relatively new, so there are no models that capture the behavior of these devices at the atomistic level, and my simulator responds to this need. So this flowchart describes some of the key components of my simulator, and I wrote my simulator in Python from scratch. And it does essentially two things. First, it computes the current flowing through the device in response to an applied voltage, and second, it computes the change in the spatial distribution of the defects, which in turn causes the conductance of the device to change. These two defect projections are examples of the kinds of results I can obtain using my simulator, and they show the internal physics of the RM. And specifically, they show the potential contours in the electric fields experienced by each defect. So now I want to talk about the current voltage results that can be obtained using my simulator. So here I'm showing the results from a single simulation where a series of write pulses are applied on the gate electrode where the top and bottom electrodes are grounded. And the pulse height is ran from negative 5 volts to positive 5 volts and then back down to negative 5 volts again. And I repeated this cycle twice. And I measured the write current during these two cycles, and this is shown over here. I also measured the read current between write pulses. And this is shown here as a function of the corresponding write pulse height. And this basically shows how the conductance is changing in response to the write operation. And the main thing I'd like to point out here is that my simulation results show strong agreement both in shape and magnitude with the experimental results reported in the literature for a device that is similar to the one that I have simulated. So with this validation, I'm going to use my simulator to compare the relative advantages of 2T and 3T RMs as synapses in neuromorphic applications. And so for this, I'm going to look at the conductance update behavior of 2T and 3T RMs under the application of fixed height write pulses on the gate electrode. And so I'm applying 200 pulses, the first 100 of which have a pulse height of positive 3 volts. And you can see the conductance is generally increasing during this phase. For the second set of 100 pulses, I'm applying with a pulse height of negative 3 volts, and the conductance is generally decreasing during this phase. And you can see the ability of the conductance to gradually increase is important for mapping weights from a neural network to a circuit in which RMs play the role of synapses. So you can see both the 2T and 3T characteristics show this gradual update behavior. However, the 3T characteristic is considerably more linear and also has a larger conductance range than the 2T characteristic. And for this reason, we expect that the 3T RM will be a better synapse in neuromorphic applications than the 2T RM. So to verify this observation, we perform a quick test in software by first training a neural network. And we use the software-determined weight matrix together with these conductance curves to create a new weight matrix of values that are realizable in RM synapses. And so we then use this hardware-adjusted weight matrix to calculate the inference accuracy, and the results are shown over here. The red curve corresponds to the 3T RM-based mapping, and the 2T RM-based mapping is shown in blue. And you can see that consistently, the 3T RM-based mapping outperforms the 2T RM-based mapping. So in conclusion, there are three main contributions of my research. First, I've developed a novel kinetic Monte Carlo simulator for multi-terminal resistive random access memory devices, or RMs, and I wrote the simulator in Python from scratch. And second, my model is fairly simple. It only captures the dynamics within the switching layer of the device, but still I'm able to obtain results that are in qualitative agreement with experimental data. And third, using my simulator, I demonstrate that the 3-terminal RM has several advantages over the conventional 2-terminal RM device as a synapse in neuromorphic circuits. And based on the promising results that I've demonstrated here, I'm hopeful that 3T-RM crossbars can enable fast, energy-efficient, and accurate artificial intelligence. Thank you very much.